Okay, so let me just recap where we were. Oops. Yeah. Okay, so I'll just recap where we were. We were looking at this um, at Rindler observers, right? And this was the closest thing that we could get to a set of uniformly accelerated observers in special relativity. Okay, and what was special about the Rindler observers is one is that each individual observer has a constant acceleration. Okay, but they have a constant acceleration in not in a particular inertial reference frame, but in their own momentarily moving rest frame. Okay, that was the first point, that each one has a constant acceleration in their own MCRF. The second point was that all these observers have to have different but constant accelerations in their own MCRFs if they are to maintain two things. One is that they are all supposed to be at rest relative to each other, okay, in their MCRF. Second is they have a fixed distance, okay, fixed proper distance between them in their MCRF. So if you preserve all these conditions, the only way to do that in special relativity is if if these observers have constant but different accelerations. Okay, so this is the closest thing that you can get to uniformly accelerated inertial observers. Okay, uniformly accelerated observers. Okay, in special relativity. So I hope this reasoning was clear for why these Rindler observers look a little different from the kind of accelerated reference frames that you see in Galilean relativity. Okay, and as we saw before, okay, so you can parameterize these Rindler observers by this trajectory. So I'm setting c is equal to 1, but ct is rho sin theta, x is rho cos theta. So constant rho are these lines, okay, these hyperbolas, and eta is the proper time. Sorry, is not the proper time. It's like a time-like coordinate. It's the proper time for one particular, or it's proportional to the proper time for one particular Rindler observer. Okay, and so these lines through the origin are lines of constant eta. Okay, and tan hyperbolic eta gives you the velocity of a Rindler observer in this inertial frame S. Okay, at any particular eta. Okay, and eta runs from minus infinity to infinity, but rho runs only from 0 to infinity. 0 being the limiting observer, okay, who accelerates with infinite acceleration and switches directions from going at speed minus c to plus c, okay, or velocity minus c to plus c. Okay, so we saw a couple of properties about the Rindler observer. So we used, the important point was that we use rho and eta. Okay, instead of talking about the coordinates of this inertial frame S, we can switch to the coordinates of the Rindler observers, that is rho and eta. And since the Rindler observers maintain a fixed distance, so if two observers are at rho 1 and rho 2, the distance between them is rho 1 minus rho 2, and that remains fixed through their motion. Okay, and that's a proper distance, which means all observers in any reference frame will calculate exactly that same distance, though they might have different ways of calculating it in their own coordinate system. It's a Lorentz invariant quantity. Okay, so now you can use rho and eta to define an accelerated reference frame in special relativity, and we were studying some properties of these Rindler observers. And one of the properties was that if we look at the space-time metric in terms of these Rindler coordinates, okay, it takes this form. Okay, it's minus rho square d eta square plus d rho square. Okay, so this is 2 points which, according to the Rindler observers, are specified by rho eta and rho eta plus d eta. Okay, which, according to an inertial observer, is specified by xt and x plus dx, t plus dt. These are the same space-time points, A and B, just referred to in different coordinate systems. One, this is in the accelerated reference frame of Rindler observers. This is in the inertial reference frame, some particular inertial reference frame S. Okay, and this is an invariant. It's a Lorentz invariant distance measure. Okay, between two Rindler coordinates, and we looked at some intuition for why it takes this form. Okay, so as we've already argued, if I fix eta, then rho or d rho, right, is the distance between these 2 points. Okay, if d eta is 0, then the distance between these two is just d rho. Okay, it's a invariant proper distance. However, if on the other hand, if we fix d rho to be 0, that is, you're looking at Rindler observers on the same hyperbola, okay, at different instants of time, then the proper time between those observers is not d eta, but rather it's rho times d eta. Okay, and therefore that is the correct invariant quantity. It's rho times d eta, not just d eta. So different Rindler observers. Okay, d eta is not their proper time, as we discussed earlier. Each one has a different acceleration and therefore a different proper time. Okay. Um, so this is something that we had discussed earlier. I won't go over it again. And as was nicely pointed out in the last class, this Rindler coordinates are very analogous to going to polar coordinates in Euclidean space. So in Euclidean space, when you switch over to polar coordinates, you get some invariant distance between 2 points is dr square plus r square d theta square. The important point about Euclidean space is that this distance measure is positive definite, right? That is, it's always greater than or equal to 0. However, in Minkowski space, the distance measure, as we already know, can be positive, negative, or 0. Okay, so with the convention that we are using for the metric, if this is positive, then the two events, the spacetime events, are space-like separated. Okay, if it's less than 0, then they're time-like separated. Okay, and if they are equal to 0, if this distance measure is equal to 0, then they are light-like or null separated. Okay, so let me just ask a question to test your knowledge of special relativity or how much you recall from the course. So if I have two events, space-time events A, so this is at some coordinate xt, this is at some other coordinate x prime t prime in the same reference frame B, and in this reference frame, okay, this event B occurs after event A, that is t prime is greater than t. Okay, is it always true that in every reference frame, event B occurs after event A? Yes or no? And yeah, and if you can explain more. Yeah, go ahead, Utkarsh.
Yeah, so if it is a time-like interval, then it will always be true that t prime will be greater than t. But if it is not, then it can be in any order.
Good. Yeah, so that's the important point. So if A and B are time-like separated, that is this invariant distance, if I calculate between them, okay, actually the finite invariant distance, which would be delta x, which is x minus x prime square minus delta t square times c square. And if this is less than 0, if it's time-like, then it will always be true that in every inertial reference frame, t prime will be greater than t. Okay, t prime converted to that appropriate reference frame. Okay, that is, they preserve their time ordering. But if events are space-like separated, okay, then it's not necessarily true. If this is positive, okay, then it's not necessarily true that these events preserve their time ordering. Okay, but that's okay because no signal can propagate, okay, from A to B if A and B are space-like separated, okay, because then it would have to travel faster than the speed of light. So causality is preserved in special relativity, okay, in the sense that even though the time ordering of two spacetime events is not necessarily the same in different coordinate systems, different inertial reference frames, cause and effect, that is, events which are spacetime events which are time-like separated, where there's a definite cause and the future event B, which is the effect, lies in the future light cone of A, then A and B always preserve their time ordering in any inertial reference frame. Okay, good. So so now, as we've seen, so this is analogous to the polar coordinates that we had written down earlier, where d rho square is like our radial coordinate. But now, if we write this in terms of the Rindler coordinates, this is minus rho square d theta square rather than plus r square d theta square. Okay, so we get an indefinite signature for the metric. Okay, that is the sign of this spacetime interval can be. So we say that this is indefinite signature. Okay, it can be positive, negative. It can be positive, negative, or 0. Okay. All right. And then the other thing, the last thing that we stopped at last time, and when we looked at the Rindler observers, is one is we noticed that the Rindler coordinates do not cover the full space-time. Okay, that's already noted that the Rindler coordinates rho and eta only describe this region of space-time here, okay, which is called the Rindler wedge. Okay, and in this Rindler wedge, the other thing that we saw is that the bounds on this Rindler wedge are basically these two light-like lines, okay, which is the line x is equal to t, or x is equal to minus t, and x is equal to t. Okay, these two ct and ct here, these two bound basically the Rindler wedge. These two light lines, okay, bound the Rindler wedge. Okay, so that's where we stopped last time. Okay, now let me just conclude with some more properties of these Rindler observers, okay, which is another property is now as I go from eta to eta plus d eta, okay, that is if I make a sort of what I think of as a time translation for the Rindler observers, what I can see is that this is actually like performing a Lorentz boost, okay, from a frame with speed v by c, which is tan hyperbolic eta. As we've seen, all the Rindler observers, okay, if I fix eta, all the Rindler observers have the same speed. They have the speed tan hyperbolic eta as measured in the frame S, okay? And I need to c times tan hyperbolic eta, and I need to make a Lorentz transform to go into the common MCRF. And the important point about the Rindler observers is that they all have a common MCRF, okay? So if I go into their common rest frame, this is the boost that I need to make. Now, if I go from Rindler observers who are at a time eta, that is, if I look at all my Rindler observers, I take the origin and I draw a line, okay, at some eta. Okay, this is x and this is t. And now I go to a different instant of time, which is eta plus d eta. Okay, so I've changed eta. So now all my Rindler observers have a different speed as measured in that original frame S. Okay, so instead of having a speed tan hyperbolic eta, they now have a speed tan hyperbolic eta plus d eta. So in effect, when I change d eta, okay, this is like a time translation for the Rindler observers, because remember eta is like a time coordinate for the Rindler observers. Okay, so time translation in the accelerated frame, that is in the frame of the Rindler observers, in the inertial frame, which is the frame S, is like going from a frame which the MCRF of these Rindler observers has a speed tan hyperbolic eta, and now I'm going to a frame S, which has where they have a speed tan hyperbolic eta plus d eta. Okay, so time translation in the accelerated frame is, if I look at it in the inertial frame, it's like performing a Lorentz boost. Okay, it's like performing a Lorentz boost. So for the accelerated observers, I'm making a time translation. For the according to the inertial observers, this is a Lorentz boost, okay, that we're making. And the extra boost is by this extra rapidity d eta. Okay, that's the extra boost that you're making. And now we see something interesting. Okay, now we know that Lorentz boosts are symmetries of the metric. Okay, that is, they leave the metric unchanged or the distance measure unchanged. That is, we know that if we look at this quantity between two space-time events, then this is invariant under a Lorentz boost, right? It preserves its form, so it becomes c squared dt prime square minus dx prime square. Okay, so this is invariant under Lorentz boosts. Okay, so what that means is the statement that this is invariant under Lorentz boosts also means that if I write out the space-time interval in Rindler coordinates, we've seen that it's minus rho square d eta square plus d rho square. Then it must be true that this space-time interval is invariant under a translation, okay? Because boosts, according to the inertial observer, are the same thing as a translation in eta as seen by the accelerated observers. So if I make a translation in eta, eta goes to eta plus delta eta. This is a constant shift, okay, of eta. Then the claim is that this interval should be the same, okay? And so you can also see why, when I look at the coefficients of this, the coefficients do not depend on eta. Okay, because if they depended on eta, then when I shift eta by eta plus delta eta, this quantity would no longer be invariant. Okay, versus d eta is invariant, right, under the shift, it doesn't change. So the fact that the coefficients are eta independent, right, is another thing that's that's telling you that this is consistent with the fact that these correspond to Rindler observers for whom translations in eta are the same thing as Lorentz boosts as seen by the inertial observers. Okay. 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 I'll pause for questions at this point, and then we'll can go ahead. Yeah, Toshif.
Sir, can you explain once more how eta going to eta plus del eta corresponds to Lorentz boost for S observer?
Yeah. So okay. So let's be clear what we mean by eta goes to eta plus del eta. Okay. So let me go back to my picture over here. Okay, so I've drawn the Rindler observers here. All these observers have the same asymptotes, right? And now what I do is I ask, let me look at a fixed eta. So what do I mean by fixed eta? Well, what we've seen is that fixed eta already corresponds to, in the inertial frame, that would correspond to, let me draw a line through the origin, okay, and this would correspond to a fixed value of eta, okay. So for all these observers, I locate them, okay, on this line, okay, and all of these observers have the same value of eta, okay, this is constant eta, okay, and now, okay, what is eta? Okay, so basically eta tells me their speed. Okay, each of these observers has a speed which is v by c, which is tan hyperbolic eta, and the speed is related to the slope of this line. Okay, so if the slope is smaller, then they have larger speeds, right? Okay, because this is t is on the y-axis rather than on the x-axis. So larger slope means a higher speed, and of course the speed is limited by the speed of light. So you can't have a slope greater than 45 degrees. Okay, and so all these observers have the same speed as measured in the original reference frame S. Okay, they have a speed of tan hyperbolic eta. And now let me locate them at a different instant of eta. Okay, that is, let me find a different instant of time. Let me call this, let me draw a second line like this. Okay, so this is eta plus some delta eta, some shift in eta. And I've located all these observers again. Okay, and I've asked what is their speed. Okay, so their speed now is tan hyperbolic eta plus delta eta. Okay, so they have a common rest frame. Okay, so even these observers at this instant of time, or this eta of eta, had a common rest frame, which I'll call S prime. And at this eta, they have a common rest frame, which I'll call S double prime. Okay, to go from S prime to S double prime, okay, I have to make a Lorentz boost by a rapidity delta eta. Okay, because all these observers, as seen in S, have a slightly larger speed compared to these observers. Does that make sense? I mean, these observers at
yes,
this
sir.
eta instant. Yeah.
Yes, sir, I get it. And sir, for in the next case, when you showed that as rho doesn't depend on eta, so if we shift eta to eta plus some del eta, so that del eta is some constant, and that is why the d of del eta is 0. So d square is invariant.
Right, ds square basically remains invariant under that shift. So that's another reason why you can see that this coefficients here of d rho and d eta don't depend on eta. Okay. Because it's a symmetry of the metric. Okay, just so it's the same symmetry reason why this metric does not change under boosts, right? Is exactly the reason why this metric, as written in Rindler coordinates, is invariant under time translations of eta or translations in eta.
Okay, sir.
Okay. Okay. Now the other thing is, as we discussed earlier. So when we had written the Rindler coordinates in terms of this quantity psi, xi, we saw that A of xi, the acceleration of the xith Rindler observer, was a over 1 plus a xi over c square. Okay, you might have to refer to the older notes. And so if I rewrite this, okay, if I bring the c square to the numerator and I write this as c square over a plus xi. Okay, so this is basically the acceleration as we've already discussed, right? Each of those Ringler observers has a slightly different acceleration so that they have the same asymptotes. Okay, so that they all have the same asymptotes. So this one is accelerating harder, this one is accelerating slightly less hard, and this one is slightly less, and so on. Okay, and this the limiting observer, that is the one who switches speed from c going to the left to c going to the right. That limiting observer has a xi coordinate of minus c square by a, and therefore they have an acceleration of an infinite acceleration. Okay, this is the proper acceleration of their observers in their rest frame. Okay, and now we can write this entire thing in terms of rho. Okay, and so the acceleration of the xith observer can now be written in terms of their rho coordinate, where rho was just c square by a plus xi divided by c square. Okay, and so the acceleration of the rhoth observer is just 1 by rho. Okay, I'm being a little cavalier with the c. Okay, I'm just setting c is equal to 1. Okay, so the acceleration of the rhoth observer I can just write as 1 by rho. Okay, if I want to be more specific, if I think of rho as a length scale, then the acceleration is c squared by rho. Okay, so this is the acceleration of the rhoth observer. So this is something interesting, right? Again, to think about with these hyperbolas, right? That we drew earlier. We know that as we go from one hyperbola to another, the rho coordinate changes, and the rho coordinate increases as we go inwards. Okay, as we go to the right in these hyperbolas. And as rho gets larger, okay, the acceleration of the rhoth observer, the proper acceleration in the rest frame, is 1 by rho, which is getting smaller. Okay, so the hardest accelerating observer is the limiting observer who goes on this light cone. Okay, then the other observers have slightly less accelerations as I go this way. Okay. So indeed, in the rho and eta coordinates, the Ringler observers are simplest to write down. Okay. Okay, now we come to something interesting. Okay, now let's look at what an inertial object, okay, that is something that's inertial as seen in this inertial frame S. What does that look like to a Ringler observer? Okay, so now imagine that you are one of these Ringler observers. Okay, that is you and let's say your friends. You're all accelerating. Okay, you're all in this accelerated frame of reference. Okay, and as we'll see, that's not far from the truth. Okay, so you're all in this accelerated frame of reference, so with the same asymptotes. Okay, and what you see is that you and your friends all have this constant proper distance rho between you. Okay, and this proper distance rho between you remains the same for all times. Okay. Can you unmute?
Hello.
Yeah, go ahead.
Yes, I just had a small sort of clarification of words. When you say accelerated frame, do you mean the frame in which we're seeing the accelerated observers or the MCRF frame of the observers themselves?
No, yeah, so that's a good question. So when I say accelerated, so the MCRF is an inertial frame. Okay, MCRF is an inertial frame, and because it describes a particular inertial frame at some instant of time. Okay, the accelerated frame is basically I'm using the coordinates rho and eta now to describe space-time events.
So accelerated is still frame S, as in the original frame in which we're looking at things.
No, no. So now imagine that I describe all now a point here in space-time inside the Ringler wedge. I can now describe by a rho coordinate and an eta coordinate. I can locate the hyperbola that it's on, and I can find out at what eta I'm looking at this point in the hyperbola.
Okay, so the asymptotes itself are what you're calling accelerated frame.
Or not the asymptotes, the hyperbolas.
Hyperbolas, yeah.
Well, yeah, you can think of it that way, or you can, if you imagine yourself as one of these Ringler observers, right, who is accelerating, and you have a bunch of friends who are all accelerating with you, right, with these different accelerations. what you're seeing is that the distance between any two of you always remains the same, right? That is the delta rho between you is always the same. Okay, and eta is some measure of your time coordinate. Okay, it's some kind of way you're using to measure time. Okay, that's passing for you. But as we've seen, if you are the rhoth observer, then the proper time that has passed for you is in some small d eta interval. The actual proper time that passes for you is rho times delta t. Okay, this is correctly your proper time. Okay, so this is your proper time, is rho times d eta. Okay, this is the amount of time that will elapse on your clock. Okay, but you use instead of using this as your time coordinate, you're using eta as your time coordinate. You're using eta as a way to measure time, because all observers, okay, that way you don't have to translate between different observers. Okay, so eta is some kind of measure of your time coordinate, and you have a fixed rho.
Okay, okay.
Okay, so now you're using this rho and eta to locate points in space-time. Okay, and now the question is, so imagine that you and your friends are trying to observe the motion of some inertial observer. Okay, so let's take this particular inertial observer. So let's imagine that there's this inertial observer who is basically at rest in some frame S. Okay, in the original frame S. Okay, and there's nothing special about this inertial frame, right? We could have chosen some other inertial frame. Okay, and you imagine some observer who's at rest in that frame. And you can imagine two possibilities. One is that that observer is in the outside the Rentala horizon. Okay, so this is the Rentala horizon. Okay, and this observer is over here. Now, if this observer is over here outside the Rentala horizon, then they will never be able to communicate. You know, at least from this time onwards, they're not, any light signal that they send will travel on a line which is parallel to this light ray. So they'll never be able to communicate with you. Okay, but on the other hand, if you look at this observer here, okay, this one, sorry. Okay, this observer here. So let me say, call this the inertial observer I. And let's watch their world line, right? So they're at rest in frame S, so only their time coordinate is changing. What you see is they are at every instant of time they're switching hyperbolas, right? So they're switching hyperbola. So they're switching from one hyperbola to another. Okay, can you tell me what is happening to the rho coordinate? Is it increasing or decreasing for this inertial observer? Rho coordinate is decreasing. What is happening to the eta coordinate?
Increasing.
Increasing. So according to you and your friends, okay, as time passes, that is, as eta increases, their rho coordinate is decreasing. Okay, which means if you imagine your rho coordinates, this is you and your friends, okay, in your accelerated reference frame. This is rho for you, okay, and this is some rho of your friend, this is a rho of another friend, and so on. And your rho coordinates go from 0 to infinity. Okay, what you see is some initial observer who is here, and then as eta time passes, okay, as eta passes, this inertial observer is drifting to the left. Okay, so the inertial observer who appeared to be at rest in frame S in the accelerated frame appears to have be moving to the left. That is, the Rentala observers as seen in frame S are accelerating to the right. The inertial observer is, in fact, if you work it out, is accelerating to the left in the Rentala coordinates. So it appears as if this inertial observer has some pseudo forces acting on it. Okay, according to these accelerated observers. Okay, so that's not surprising, right? When we know from Newtonian mechanics, right, that if you're in an accelerated frame of reference, then you will get pseudo forces, and inertial objects will appear to experience these pseudo forces. So in fact, this object will appear to accelerate, okay, towards the rho is equal to 0 point. But the interesting thing is, okay, for this inertial object, once it reaches this horizon, okay, for the Rentala observers, there's nothing special, okay, about this point for this inertial observer. For the inertial observer, their world line will just continue. Okay, they will just keep going. Okay, they just keep going. They're sitting at rest at the same point. Okay, but according to the Rentala observers, that is you and your friends, okay, once this object crosses this horizon, okay, it can no longer communicate with you. Okay, any signal it sends cannot travel fast enough to catch up to any of you or your friends. Okay, so once it crosses this point, any signal that it sends will never reach the Rentala observers. Okay, so that's quite remarkable, right? That's something that's unusual from the point of view of Galilean relativity. Okay, so the existence of this horizon is something quite unusual. Okay, um, okay, so this inertial object experiences acceleration, experiences pseudo forces as you would expect. Okay, and it experiences the pseudo force in the direction which is opposite to the direction of acceleration. So the Rentala observers are accelerating this way. According in the accelerated frame, the inertial observer appears to drift to the left, okay, towards decreasing rho. Okay. So here are those points in words. So the inertial object would appear to accelerate in the rho coordinates, okay, and the rho coordinate would go on decreasing. Okay, so this would be like the pseudo force that inertial objects experience, okay, in the accelerated frame. And as time goes to infinity, okay, according to the Rentala observers, here's another interesting thing. If you ask what is the eta at which this inertial object will cross the horizon, what you will find is that, okay, all of these lines have different etas, right? But this line, this light ray, has eta is equal to plus infinity. Okay, which means according to the Rentala observers, this object I never crosses that horizon. Okay, it takes an infinite amount of time or infinite eta to actually get to that horizon. Okay, so that's also something quite strange. Okay, so for the Rentala observers, it just seems like this object is getting there, getting close to rho is equal to 0, but never quite crossing it. Okay, it just takes an infinite amount of time to actually get to this point. Okay, to the rho is equal to 0 point. So that's another thing that's strange. Okay, as eta goes to infinity, the object would seem to disappear beyond the Rentala horizon, except that eta is equal to infinity never comes for the Rentala observers. Okay. However, for the inertial object, okay, according to the inertial object, if they are carrying a clock with them, they will see that in a finite proper time, as measured by this time interval, okay, in this finite proper time, they will just cross according to their clock. In a finite time, they will cross into this Rentala horizon, cross the Rentala horizon. They don't yet know it's a Rentala horizon because they have no way of communicating with the, well, unless they've communicated with these observers, they don't really know there's a Rentala horizon here. But once they cross this point, they have no way of communicating with any of these Rentala observers, okay? Because all of these observers are accelerating so fast that no signal will ever reach them, okay, from this inertial observer. This would happen in a finite proper time, after which they would lose contact with all the Rentala observers. And this is very similar to what happens in a black hole horizon. Okay, when you fall into a black hole, you can no longer communicate with objects outside. You don't experience anything unusual. You're just like an inertial observer, right? As we've discussed, free fall in a uniform gravitational field is just like being an inertial observer. So you would not even know that you're falling into a black hole. Okay, of course, there's some caveats to this, but as you fall into a black hole, if it's sufficiently big, you would not realize that you're falling into a black hole. And as you fall into the black hole, you lose your ability to communicate with observers outside the black hole. Okay, and this unusual thing can already be understood in special relativity. Okay, and the interesting thing is the inertial object here, unlike in a black hole, the object here will just see, even as it crosses the Rentala horizon, you notice nothing unusual forever. Okay, as your life continues as normal, right? You don't care that these Rentala observers have accelerated fast and gone out of existence as far as you're concerned. Okay. Okay, the other thing is, suppose you do try to communicate with the Rentala observers before you cross the horizon. Okay, so before you try to cross the horizon, you try to communicate with them and you try to send them signals. So let's imagine that you send light signals. Okay, so you send light signals and light signals travel at 45 degrees. So they'll travel on this 45-degree line, and at later times also they'll travel on 45-degree lines. Okay, so you'll send a light signal and you'll send a light signal of, let's say, some frequency. Okay, so let's say you shine a torchlight and you shine visible light at them. Okay, and you try to send the signal towards the Rentala observer. Now, as you get closer to the horizon, okay, your signals reach these observers later and later, because as you're getting closer to the horizon, you're getting closer and closer to that asymptote. Okay, and the light signal that you send will travel on a line which is parallel to that asymptote. Okay, and that light signal is now getting very close to that asymptote. So it's going to take longer and longer to actually intersect any one of these Rindler observers. Okay, so to intersect this Rindler observer, it will take a very long time. So this Rindler observer will see it much later. And because they see it much later, as measured in frame S, this Rindler observer is now traveling much faster. They're much closer to the speed of light when they receive the signal. So they're much closer to the speed of light, again, as measured in the frame S. Okay, so what that means is the light signals which are sent from the inertial object to the Rindler observer, they will continue to reach the Rindler observer as long as they are sent before crossing the horizon. Okay, the inertial observer has to, any signal that they send before crossing the horizon will definitely reach the Rindler observers. It might just reach them after a very long time. Okay, and the other thing is that these light signals, they will get more and more redshifted as they reach the Rindler observers. Okay, why is that? Well, we know that if you are sending a signal and you are at rest, okay, as measured in this frame S, and there is an observer who's traveling away from you at a very high speed, okay, when they receive the light signal from you, the light signal will appear to be redshifted. Okay, as we studied in STR, okay, the observed frequency will be the emitted frequency times this factor, 1 minus v by c over 1 plus v by c raised to half. So if v goes close to the speed of light, okay, the observed frequency that this observer receives will go to almost to 0. Okay, which means if you send visible light, okay, depending on how late this observer receives it, they're traveling very fast and getting closer to the speed of light. That visible light will become long wavelength, it'll become microwave, then radio wave, and so on. Okay, and you'll get stretched to longer and longer wavelengths. Okay, so basically, as you're crossing the Rindler horizon and you're trying to communicate with these rapidly accelerating Rindler observers, okay, the signals that you're sending them will reach them later and later. Okay, and the signals will get shifted to lower and lower frequencies. Which means like, maybe they won't have the capability to detect them, okay, because they're very long wavelength light. And finally, when you cross the horizon, any signal that you send will never reach those Rindler observers. Okay, so this is something that's quite strange, and it's very analogous to what happens as you fall into a black hole. As you fall into a black hole, you can try to screen by sending out these light signals. Okay, and going on trying to communicate and saying, I'm falling into the black hole, I'm falling into the black hole, I'm falling into the black hole. You can go on sending information in Morse code or any other kind of code. You can go on communicating with observers outside. And for the observers outside, okay, the signals that they receive from you will always reach them in a finite eta. Okay, and in fact, they will never see, they'll see you approaching the horizon slowly, but they'll never quite see you crossing the horizon. Okay, for them, for these accelerating observers, they will wait till an infinite amount of eta has passed for them. Okay, and then you cross the observer, okay, you cross the horizon, but that never happens. Okay, and all the signals that you're sending to them, all these signals that you're sending to those observers who are far away, all of those signals are getting redshifted. Okay, so anything that you send is getting stretched to longer and longer wavelengths. The closer you get to this Rindler horizon, okay, the more stretched those signals are to any particular Rindler observer. Okay, and now here's the important point. Okay, now let's connect back to the equivalence principle. So if you think of the pseudo forces in the Rindler frame, okay, the pseudo force being the acceleration experienced by this inertial observer as seen by the Rindler observers. Okay, so the Rindler observers are an accelerating reference frame. In that accelerating reference frame, something that was an inertial observer, like I over here, this inertial observer appears to experience pseudo forces. Okay, and you can think of these pseudo forces as being kind of like the pseudo forces due to a uniform gravitational field. Okay, because as we discussed, the Rindler observers are as close as you can get to uniform acceleration. So in special relativity, the experience of an inertial observer, the pseudo forces that they're feeling as seen in this accelerated reference frame, are very much like a uniform gravitational field. That's exactly what you'd call a uniform gravitational field. Okay. So you can think of the inertial objects as freely falling observers in a uniform gravitational field. Okay. So so let's see what that means. Okay. So if you go back to this picture that we drew earlier. Okay, so you're in a lift, okay, and let's attach a coordinate system to this lift. Okay, so this is, let's say, your x, y, and you have to attach a time coordinate as well. But I attach it, so actually let me call this x. Okay, and this is, so my origin is fixed and it's fixed to the lift. Okay, that's what I mean by being in an accelerated reference frame, and the lift itself is accelerated. Okay, so the lift itself is accelerated. So I'm in the lift, my apple is in the lift, and we're both being accelerated. Now the apple is an inertial object. Okay, that is, it's not being acted on by any forces as seen in this inertial frame S. Okay, in which this lift is appearing to experience this acceleration. So now if I go into the frame of the lift, this is like, so observing this situation is like being in frame S. Okay. Now what we're saying is we're going into this accelerated frame. Okay, we're going into the frame where the lift coordinates are fixed. Okay, so we're fixing a rho coordinate here. This is our rho is equal. So this is, let's say, our rho is equal to 0, and this is our rho is equal to some rho naught, and which is attached to the lift. Okay, and these are our accelerated coordinate system. And now this inertial object, which is the apple, okay, which is like I, okay, this object is just hanging in free space, right? Because that's what you would expect as seen in this frame S. But in the accelerated frame, since the lift is accelerating upwards, okay, relative to this origin in the lift, okay, this is your x is equal to 0 coordinate, the apple is falling downwards. Okay, the apple is experiencing a pseudo force. So the apple is falling this way. So the inertial object is falling towards the Rentala horizon, okay, which is at rho is equal to 0. So if you imagine that this apple was a person trying to communicate with the person in the lift who is attached to the lift, or let's say attached to the lift, or let's say holding onto the lift, then they would send light signals. But at some point when they cross the Rentala horizon, okay, the lift is accelerating so fast, as seen in the frame S, that any light signal that this apple sends will not be able to catch up with the lift, okay, or will never be able to reach any of the lift observers, okay. So basically that that rho is equal to 0 point is the point of no return, where no signals will ever reach these Rentala observers. Okay, and by the equivalence principle, these two things are completely equivalent. Okay, acceleration, uniform acceleration, is equivalent to this situation where you have pseudo forces, and these pseudo forces can be thought of as a uniform gravitational field, where the strength of this gravitational field is exactly equal in magnitude, equal in magnitude but opposite in direction to the acceleration of the lift. Okay, so is this clear? This analogy between, or basically what we did was to go from acceleration in Newtonian mechanics to accelerated reference frames in special relativity. And what we've seen in special relativity is that there are peculiar features of accelerated reference frames in special relativity. Okay, like the existence of Rentala horizons. Okay, that's something that you don't expect in Newtonian mechanics. Okay, and now we're using the fact that an accelerated reference frame, a uniformly accelerated reference frame, is exactly equivalent to a uniform gravitational field. Okay, you cannot tell the difference between the two things. Okay, so if you were in a gravitational field, a uniform gravitational field, okay, and there were objects that were falling, okay, and we are in a uniform gravitational field, right? Where, let's say, to a good approximation, let's say we are at the surface of the Earth, we're in a uniform gravitational field, and we are really the ones who are prevented from falling. Okay, so we're not freely falling in this uniform gravitational field, but if you hold an object and you drop it, that object is freely falling in the Earth's gravitational field, and therefore that object is actually inertial. We are not inertial. Okay, we are being held up by the surface of the Earth. Okay, so in this way of looking at it, okay, we are not the inertial observers. The apple that's actually falling, that is the inertial observer. Okay, or that's an inertial object. Okay, again, I'll pause for questions here.
Hello, sir.
Yeah.
Sir, in black hole analogy that you made earlier, that a person is falling into the black hole, and he's an inertial observer, and he's sending a signal to an accelerated observer. Uh, so even if it wasn't a black hole, the result would be same, no?
Even if it wasn't a black hole, yeah, result would be the same. That's what I'm saying. I mean, you don't have to see any of this using black holes. You can just look at Rentala observers who are uniformly accelerated. There's no black hole or anything like that here, right? It's just talking about a bunch of accelerated observers and an inertial observer in frame S.
Okay. No, I got confused between since there was a event horizon of the black hole itself, and also the observer that we took was accelerating. So
Okay, so let me tell you exactly what the analogy is. See, if you consider a black hole, let's imagine that there's a region. Okay, let's imagine that there's some point mass here, and this point mass has a gravitational field. Okay, and basically beyond this region, which is the black hole horizon, which I just explained in the earlier class, but I not proved this. Okay, which we'll see later. So there's some radius beyond which the escape velocity is. So if you're inside this region, the escape velocity is sorry, at this surface, the escape velocity is the speed of light. Okay, so now if you enter this region, okay, if I want to send a light signal, that light signal will never escape because that light signal that you shoot up will fall back inwards due to the gravity of this massive object at the center. Okay, so anything that you try to send out from this region will fall back. Okay, it will not be able to escape the black hole. Okay, now the analogy is the inertial observer is any object outside the black hole that's falling into the black hole and crosses the horizon. Okay, crosses this region. The accelerated observer is an object that is sitting, hovering outside the black hole. Why is this object accelerated? Well, if it were actually inertial, it would be in free fall in a uniform gravitational field, as discussed earlier. So it would be in free fall. To prevent it from being in free fall, to make it hover, you have to actually accelerate it in the opposite direction. Okay, so this is basically a non-inertial object. Okay, so if you're outside a black hole and you're not falling into it, you are a non-inertial, you are an accelerated observer. Okay, and this inertial object crosses the horizon of the black hole and falls inside. Okay, and this horizon of the black hole is similar in some ways to this Rentala horizon.
okay, so now I got it.
Other questions? Yeah, Tosha?
Sir, in the earlier diagram, can you explain once of what observer S sees?
This diagram?
Yes, sir, this diagram.
Okay, so let me explain. Let me just draw it here. So here's the lift. Here is person. Here's the apple. Okay, this is frame S. Okay, so as we discussed, if you're in an inertial frame and there are no forces acting on any objects, then everything will just hover, right? Everything will stay exactly where it is, right? The apple will float in the air. Now imagine that the lift has a hole here. Okay, the person is standing on the lift. Okay, so if the lift moves up, they will also move up. Okay, and the lift itself, okay, you can imagine some coordinates attached to the lift. These are not the coordinates of the observer S. The observer S has their own coordinates, okay, which are not attached to the lift. And so they have a fixed x is equal to 0, and they define, the lift is now at x is equal to some x naught. Okay, and now as the lift accelerates upwards, okay, what they will see is that the lift is moving upwards. So at the next instant of time, the lift will be here. Okay, the person is being pushed by the lift and they've gone up. The apple has stayed exactly where it was because there's no forces acting on the apple. Okay, the apple is an inertial object. The person in the elevator, what do they experience? So imagine that you're now in the elevator, you can't see anything else but this apple and the lift. Okay, what do you experience? Well, you experience this. You are here, and that apple is now here relative to you. Okay, so the apple has fallen. It's experiencing a pseudo force. It's experiencing the force of gravity. You could call this the force of gravity. There's no way to distinguish.
Yes, sir, I got it.
Other questions? Yeah, Malvika?
So can we say that the accelerated frame is the um, frame in which the space-time coordinates of the Rindler observers are fixed? So the Rindler's observers own space-time, like they have their space-time
Well, each
coordinates.
one has a fixed rho coordinate, but their eta coordinates are changing.
Yes, sir, but that isn't frame S.
No, no. That's so in frame S, you're labeling them by their x and t coordinates. Okay, and t is equal to rho cos eta, and x is equal to t is equal to rho sinh eta. So this is the motion of a Rindler observer as labeled by the coordinates t and x in frame S. So tx really refer to the coordinates of the frame S. Okay, and this is the motion of a Rindler observer as seen in that frame S. But now what we're arguing is that in the Rindler wedge, you can label space-time points instead of labeling them by their t and x coordinate, you can label them by a rho and an eta coordinate. That is the accelerated coordinate system.
So yeah, it's an accelerated coordinate, but it's still an accelerated coordinate like system. It's sort of okay. Who is it moving with? That's my question.
It's moving with the Rindler observers. The Rindler observers, they maintain a fixed rho between them, right? So as seen in their common MCRF, they will always see a fixed distance delta rho between any two Rindler observers. And their time coordinate goes on changing as eta changes.
Yeah, so that was the question. Thank you.
Okay, any more questions? Okay, so now what we'll do is we'll take the lessons that we learned from Rindler observers, okay, and we'll try to see some hints of general relativity, okay, that we can learn from these Rindler observers, okay. So we'll kind of get a glimpse of what's going to come ahead. So one of the things that we've seen is that when you make a coordinate transformation like this, okay, that is when, just like Malvika asked, right, you went from a coordinate system of inertial observers to some other coordinate system, okay, of this Rindler observers. So we went from the pair of coordinates tx to the pair of coordinates rho eta, okay, and as long as you're in the Rindler wedge, okay, this is a one-to-one transformation. Okay, you can go back and forth. Okay, and within that Rindler wedge, we saw that you can write the line element, that is the space-time interval or ds square. You can write it in terms of some kind of metric, g alpha beta times dx alpha dx beta. Okay, in inertial reference frames, ds square is always dt square or minus dt square plus dx square plus dy square plus dz square. That is your metric g alpha beta. Okay, is just what we call the flat space metric or Minkowski space metric, minus 1, 1, 1 with zeros everywhere else. Okay, what we're kind of seeing with the Rindler observers is the basic idea of general relativity, which is that the metric itself can be coordinate dependent. Okay, the metric itself can be coordinate dependent. So the metric coefficients are coordinate dependent. So when we wrote the same metric in terms of the rho eta coordinates, we got something like rho square d eta square plus d rho square. Okay, so the coefficient was rho dependent, or if I write the coefficients as a matrix, right, it looks like this. It looks like minus rho 1, 1, 1. Okay, I'm just doing it in 2 dimensions, so it's just minus rho 1. Okay, so it's not a constant. It changes as I change my row coordinate. Okay, this metric changes as I change my row coordinate. So that is something we're going to see a lot in general relativity. In fact, in general, the metric coefficients can depend on all the space-time coordinates. Okay, they can go on varying. Okay, so this is something that we'll see later. The other thing is that Rindler observers, okay, are like uniformly accelerated observers. So going into an accelerated reference frame is exactly as we've discussed by the equivalence principle, like being in a uniform gravitational field. Okay, so the effect of gravity, or equivalently the effect of an accelerated reference frame, a uniform gravitational field, or an accelerated reference frame, this effect can be removed. Right? There is no way to tell. The equivalence principle is that there is no way to tell the difference between uniform acceleration or a constant gravitational field. Okay, so as we've seen, you can remove the effect of this gravitational field or this accelerated reference frame. That is, you can go away from the coordinate system rho eta. You can go away from this accelerated set of coordinates to the inertial set of coordinates by just a simple coordinate transformation. Okay, so you can get rid of all these weird effects of acceleration of inertial observers, the observer I being accelerated in the rho eta coordinate system. You will not see that if you go to the inertial coordinate system. The inertial object will appear to be inertial. Okay, so what that means is for the metric g alpha beta. Okay, if I am in an accelerated reference frame, a uniformly accelerated reference frame, I can always find a coordinate system so that g alpha beta in the new coordinate system gets transformed to this eta alpha beta, which is called the Minkowski metric, which is just minus 1, 1, 1, 1. Okay, so I can always find a coordinate system. So I went from g alpha beta in the rho eta coordinate system to eta alpha beta in the tx coordinate system. Okay, and in the tx coordinate system, this metric is this minus 1, 1, 1, 1. Okay, so this is called the Minkowski metric. Now, this is true as far as uniform gravitational fields go. Okay, so as long as I have uniform gravitational fields, I can always get rid of this metric, which is like for Rindler observers, by transforming to an appropriate inertial coordinate system, and I will get the Minkowski metric. Okay, so I can work in this preferred set of coordinate systems, which are the inertial reference frames. Okay, so there's a preferred set of reference frames, which are the inertial reference frames in this case. Okay, however, this is not true when you have non-uniform gravitational fields. When you have non-uniform gravitational fields, those non-uniform gravitational fields are like what we should really think of as genuine gravitational fields, okay, as opposed to these fake gravitational fields, which are caused by uniformly accelerating frames of reference. Okay, so it is possible to have non-uniform gravitational fields. Okay, and if you have a non-uniform gravitational field, then it is not possible to always get rid of the coordinate dependence of the metric. That is, the fact that this metric in some coordinate system depends on the coordinates. Okay, it's not possible everywhere in space-time to simultaneously switch off the coordinate dependence by just switching to a particular coordinate system. Okay, that is, it's not possible to get the Minkowski metric just by a change of coordinates everywhere in space-time. You might be able to do it in one region of space-time, but if you do it in one region of space-time, in some other region of space-time, g alpha beta will become coordinate dependent. Okay, so the fact that g alpha beta depends on your coordinates is not something that you can get rid of everywhere in space-time. When that happens, then you say that your gravitational field is non-uniform, and this is a true effect which you cannot get rid of just by changing your coordinate system. Okay, So Rindler observers are a special case of uniform acceleration. Uniform acceleration, if I just change my coordinate system, I can see that it's the same as an inertial reference frame. Okay, so instead of being in this accelerated frame in a uniform gravitational field, I can always switch to an inertial coordinate system S. Okay, the claim is if you're in a non-uniform gravitational field, you cannot make this switch to an inertial reference frame simultaneously at all space-time points. Okay. The other thing, okay, one other feature that we've seen is that the coordinates, according to the Rindler observer, they appear to be ill-defined as rho goes to 0. Okay, so for example, we've seen that as rho goes to 0, ds square is equal to minus rho square d eta square plus d rho square. Okay, so this is very analogous to the coordinate singularity that happens in polar coordinates. So in polar coordinates, we've seen that the line element is r square d theta square plus dr square. Okay, so the problem is that r is equal to 0. If I change my angle by some amount d theta, okay, well, actually the problem is at r is equal to 0, how do I specify what the coordinate is? What is the theta value of this coordinate, right? Is theta equal to 0? Is theta equal to 2 pi? There's no smooth way, right, to continue the coordinates, the coordinate system r theta down to this point, okay, to the r is equal to 0 point. So I typically exclude this point, but it doesn't mean that this point doesn't exist, right? It's just in polar coordinates, it's awkward to talk about this point, okay? So this is called a coordinate singularity, okay? But there's nothing wrong with this point. It's just that my coordinate system doesn't adequately describe that point, okay? And so this coordinate singularity is not a physical singularity, okay? There's nothing physically strange about this point. It's just like any other point in flat space, okay, in Euclidean space. So this is just an artifact of my coordinate choice, okay, which means it's some strange thing that seems to appear, but it's only in my equations, but that's only because my coordinates are a bit weird, okay. So you will encounter these kind of coordinate artifacts, but you basically can switch coordinate systems and then the coordinate artifact goes away. For example, if I go to flat coordinates, just xy coordinates, the same line element instead of in polar coordinates, it just looks like this, and then there is no coordinate singularity. Okay. Okay. The next thing is that the full space-time. Okay, so again, this is something that we're learning from Rindler observers. The full space-time, okay, may not be accessible to the Rindler observers. For example, we've seen that the rho eta coordinates of Rindler observers, they only cover the Rindler wedge. They don't cover the full space-time. In fact, a Rindler observer would never know if you've gone past their Rindler horizon, because according to them, it takes you an infinite amount of time. Eta goes to infinity before you actually cross that Rindler wedge. Okay, but the inertial observer who crosses that Rindler horizon, or if I can think of these inertial observers as freely falling observers in a uniform gravitational field, these inertial observers can explore the full space-time. They can go beyond the Rindler horizon. Okay, so the full space-time can be discovered by freely falling, or what we call a locally inertial observers. Okay, in some region of space-time, they are like inertial observers, and they can explore beyond these kind of horizons. Okay, so the freely falling observers can just explore the entire space-time by just not doing anything. Okay, they will end up exploring the full space-time. Okay, whereas the Rindler observers will not. Okay, the accelerated observers may not see the full space-time. The second thing, okay, so one more point is about the light cones of these Rindler observers. Okay, so as we've seen, so in the Rindler coordinates, ds square is equal to minus rho square d eta square plus d rho square. Okay, so what do we mean by light cone? Well, light cone means light will travel along the path for which ds square is equal to 0, right? We know this from inertial reference frames, for example. Light will follow the path for which this quantity is 0. Okay, so in Rindler coordinates, what it would mean is light would travel a distance such that this is 0, or in a time d eta. Okay, this is Rindler time. Okay, it would travel a distance d rho and d eta and d rho would be related in this way. So if you are at a different rho coordinate, okay, the amount of d rho that you travel in a given d eta, okay, depends on how much what your rho coordinate is. If your rho coordinate is larger, you will travel less of a d eta distance. Sorry, less d rho in the same d eta. Okay, so if your rho is larger, d rho is also large. Sorry, d rho is also larger, so that d eta is the same. Okay, so in a given d eta, in a given time interval, you want to preserve this quantity. So if your rho quantity is larger, your d rho is also larger. So you'll travel a larger distance. Okay, larger as measured in Rindler coordinates. So if I look at this in terms of Rindler coordinates, so if I look at a rho coordinate here and an eta coordinate here, okay, if I take rho is equal to 1, okay, then d eta is equal to d rho. Okay, so my light cone is like at 45 degrees. Okay, because on this 45-degree line, I will travel a distance d rho in a time d eta. Okay, so this is like a 45-degree line. Now, if I go to large rho, okay, then the distance d rho that I travel in the same amount of d eta will be larger. Okay, so my light cone kind of opens up. I cover in the same d eta, I cover a larger d rho. Okay, and and in fact, as I go in the opposite direction, the light cones close up. Okay, which means in the same d eta, I cover a smaller d rho. And in the limiting case of the rho is equal to 0 Rindler observer, okay, my light cone actually shrinks to 0 size. Okay, that is in a time d eta, okay, the d rho that I cover is 0. Okay, that is I don't actually travel any distance at all. Okay, I cannot change my rho coordinate. That's because you're at the Rindler horizon. Okay, so another way to think about this is effectively, okay, if I think of this as my time coordinate, okay, I can think of this as if I measure distances using d rho and I measure times using d eta, then effectively by comparing these two equations, I can think of rho as my effective speed of light. Okay, and what that means is just by comparing these two quantities, rho is like my effective speed of light. So that means if my rho coordinate is larger, my speed is larger, and therefore these light cones are opening up. And if rho is smaller, or in the limit rho goes to 0, right, my speed is decreasing and the light cones close up. Okay, so the effective speed of light as measured by this Rindler observer, you can think of as something like c by rho. Okay, and finally, we'll talk about the existence of horizons. Okay, so this is something that's unique to special relativity. So if you look at the past light cone of any Minkowski observer, so if you take any Minkowski observer, this is x and t, and if you wait long enough, so when they're in the far future, okay, and you look at their past light cone, okay, their past light cone will cover almost all the points in space-time. Okay, if you wait long enough, a Minkowski observer, that is this inertial observer in Minkowski space, they will be able to receive signals from every single point in space-time. There's nothing stopping them from receiving signals. Okay. However, as we've seen, if you look at a Rindler observer, the past light cone of a Rindler observer, it only covers half the space-time. Okay, that is, they will not be able to get signals from everywhere in space-time. The Rindler observers, okay, they will be able to get signals from everywhere on this side of the Rindler horizon. Okay, on the other side of the Rindler horizon, they cannot get any signals. Okay, so even someone who is, let's say, here, okay, who's not on the Rindler observers, if they send a light signal, this light signal will reach the Rindler observers eventually. But someone here, if they send a light signal, this will never reach the Rindler observers. Okay, it will travel parallel to their horizon. Okay, so this kind of feature where the observers themselves, so that is the Rindler observers themselves, experience a horizon is called an observer dependent horizon. Okay, so this horizon, just like the horizon for a black hole, is observer dependent. Okay, if you're accelerating or hovering outside a black hole, you will see horizon. If you fall into the black hole, you don't see horizon. Okay, you just fall into the black hole and you experience life as an inertial observer. Okay, so these are some features that we will see, okay, which will show up later again and again through this course. Okay, so let me just recap the features. One is a metric which is space-time dependent. And in a true gravitational field, that is not a fake gravitational field like that of Rindler observers, this metric, okay, you cannot make the metric space-time coordinate independent at every single point in space-time. Okay, it's just not possible to do that. That is a signature of a true gravitational field. We'll study more about what this means soon. The other thing is sometimes your coordinates might appear to be ill-defined, but this is not necessarily a feature of gravity or anything like that. That's just a feature of your coordinate system. Okay, you might switch to a coordinate system in which you don't find these artifacts at all. Okay, and the full spacetime can be discovered by freely falling objects like these inertial objects, okay, who can explode beyond the Rindler horizon. And the light cones of the Rindler observers, they close up as you get close to the Rindler horizon. Okay, that is, you are not able to travel very large Rindler distances, rho, okay, in time deta, as if you're closer and closer to the Rindler horizon. And finally, that Rindler observers have horizons, okay, and these horizons are observer dependent. Okay, some observers in the same space-time, some observers may experience a horizon like the Rindler observers, but other observers, like the inertial observers, do not experience any horizon. Okay, so these are some peculiar features that we will see in general relativity, but these features already exist in special relativity. Okay, so that's kind of what I wanted to convey. Okay, any questions here before I move on to the next thing?
Sir, I don't quite understand why the point of coordinate singularities is particularly troubling us, because I'm probably like jumping a bit ahead, but if we come to manifolds, etc., we anyway define coordinates only locally, so we can always.
Yeah, that's the point, but it's just it's not. It's just to mention that that coordinate singularity should not be troublesome. That's all I was trying to say. There's no reason to worry about coordinates looking strange, right? I might switch over to another coordinate system, so in which I find nothing strange. I was just repeating exactly what you said.
Yes, sir.
Okay, anything else? Any other questions? Okay. Okay, if not, then let me just move to the next part. Okay, which is okay, so what I'm just going to try to do before I actually get into the details of general relativity is I'll just tell you what have we learned and what principles of general relativity can we learn from this. Okay, so before we do that, I just want to ask and answer one question, which is suppose we just take inertial observers. So forget everything that we did about Rindler observers now. Just let's look at inertial objects. Okay, in a reference frame S. Is there a way to describe the motion of these objects? Okay, that is motion of inertial objects who experience no forces. So there's no forces acting on them. Okay, but we want to describe their motion in a way that is sort of independent of the particular reference frame that they're in. Okay, so what we've seen is if I take an object which is inertial, for example, we can take Newton's law. So m times proper acceleration is equal to 0. This is the law of motion in some particular reference frame S. Okay, and of course we can transform it into another reference frame, but what we really like is some kind of Lorentz invariant way of describing it, not something that changes from one reference frame to another. But of course we can use the dictionary of special relativity and translate this to some other inertial frame S prime. But is there some way of capturing the same physics, okay, in a way that is Lorentz invariant? Okay, that is in some way where all observers in all inertial frames don't write it in any other way. Their dictionary gives them exactly the same answer, not even in the same form, but exactly the same answer. Okay, that is, if I write it in a different frame, I can write it like this. This has the same form, but it has different coordinates. Okay, the coordinates here are x prime. Okay, so what I want is, in other words, I have a vector, and this Lorentz 4 vector transforms from one frame to another. I want a quantity which is a Lorentz scalar, okay, which captures the information of the motion of this particle. Okay, so let's see how to do that. Okay, and one other thing that you can do is you can write this in terms of this 4 acceleration in terms of the 4 velocity. So you can write this instead of the second derivative of position, you can write it as the first derivative of 4 velocity. So you can write it as du alpha d tau is 0. Okay, and so the statement of what is the motion of an object when there are no forces acting on it is that its proper velocity is constant. Okay, in some frame S. Okay, and that constant is different. I mean, it's a different 4 vector in some other frame S prime. Okay, so dx alpha d tau is a constant. This is the proper velocity. And if I solve this equation, it tells me that the change in x is proportional to proper time, and delta t is also proportional to proper time. Okay, which means that the speed of the object, which is delta x by delta t, as measured in some frame S, this is a constant. Okay, so that's not surprising. If there's an inertial object which has no forces acting on it, then what should it do? It should travel with constant speed. Okay, it's just that the equation to see this is more complicated in special relativity than it is in Galilean relativity. In Galilean relativity, you directly have this equation. In special relativity, the equation boils down to this. Okay, but what you find is the same thing. V is constant. Okay. Okay. Now the only thing is, for consistency, with causality, you need the speed of the particles to be less than the speed of light. Okay, that's not a constraint that you're going to get from this equation. Okay, but let's assume this additional constraint. Okay, and then if we draw the space-time diagrams for a particle on which no forces are acting. So suppose the particle is at x is equal to 0, at t is equal to 0. What are the possible trajectories for such a particle? Okay, so if I'm in some inertial frame S, I can draw the light cone here. And the trajectory for such a particle would always be, some straight line, which lies within the light cone. Okay, that would be, so it would be either this line, this would be one speed, or this would be a different speed. Okay, and an infinite line. Okay, it would extend forever. Okay, and now let's ask a different question. Okay, so suppose we go to a particular frame. Okay, that is, we take this particle, but now let's, instead of being in some general frame, let's go to the rest frame of this particle. Okay, so we'll go to the rest frame. In the rest frame, the motion is just like this. Okay, along the t prime axis, but not along the x prime axis. So this is the rest frame of the particle. And now, given that the particle started at A and ended in B, okay, you can try to draw all possible trajectories that the particle can take to get from A to B. Okay, so one possible trajectory is this trajectory, which is the one it actually follows, which satisfies the equations of motion. Other possible trajectories are this one, for example, right? It goes like this. Okay, so this we'll call this trajectory 2. Now, what is the difference, the key difference between trajectory 1 and trajectory 2? Okay, trajectory 2 must be an accelerated trajectory, right? Because it has to turn, okay, and come back to this point. Okay, so trajectory 2 is an alternative object that gets from A to B, but it has to be an accelerated object. Okay, now what should happen for an observer moving on trajectory 2 is that their proper time, okay, that elapses between getting from A to B is going to be smaller than the proper time of object 1. Okay, one way you can imagine this is, let's imagine the extreme limit of object 2, that is, it travels along light rays. So it travels like this, or very close to light ray. So the proper time that would elapse would be 0 or nearly 0, and then it turns back, and then the proper time that elapses would be nearly 0. So the proper time that object 2 experiences can get arbitrarily close to 0 as you want, okay, by making it go faster and faster. So in fact, any trajectory that you draw, okay, that gets from A to B, that is not this straight line trajectory, okay, it is going to have a shorter proper time than the straight line trajectory from A to B. Okay, so trajectory 2 will experience a shorter proper time than object 1. Okay, and this is familiar to you from the twin paradox. Okay, from the twin paradox, if you imagine that object 1 and object 2 are twins, Okay, which twin ages more? The answer is the accelerated twin always ages less than the unaccelerated twin. Okay, so the unaccelerated twin, that is object 1, will always experience the longest proper time of any object that gets from A to B. Okay, so given that the object gets from a spacetime point A to a spacetime point B, okay, the claim is that an inertial object will always take the path through spacetime that maximizes its proper time. Okay, so an inertial object will always take the path through spacetime that maximizes its proper time. Now, this statement is a different way of restating the same equation that we had. Okay, but this restatement of this equation in this way allows us to say something which is a Lorentz invariant statement. That is a statement which is sort of frame independent or is a scalar in all reference frames. Okay, so this statement can be made Lorentz invariant. Okay, and the way to say this is the proper time that a particle experiences is just this. It's the spacetime interval, which is eta mu nu dx mu dx nu. The minus sign is because of the signature of the metric we're using, and you take the square root of that. So this is the proper time. Okay, the only requirement is that d tau square is positive, okay, or d tau is real, okay, because it has to travel on a time-like trajectory, which is the same thing as saying v is less than c. So this, as we discussed, is not something that comes out of this equation. You have to impose this condition that the trajectory is time-like. Okay, but once you impose this condition, that is, you impose the condition that this quantity is positive. Okay, well, the quantity under the square root is positive, always a good thing to have. Eta mu nu, if it's of the form -1, 1, 1, okay, which is our the metric convention that we're using, then the claim is that this d tau, okay, is maximized, okay, when I get from A to B, okay, from any two spacetime points A to B. If I want to find out what is the trajectory of an inertial object that gets from A to B, it's the one that maximizes d tau. Okay, and or equivalently, it's one that solves this equation of motion. Okay, now I can write d tau. Okay, so I can define this quantity. Okay, and as a precursor to this, you can see that this is what we'll call the action of the particle. So S, the action, will be a function of the spacetime coordinates. The spacetime coordinates are functions of the proper time. Okay, so just this is like a parametric way of parameterizing the trajectory. So as I get from A to B, I just integrate the proper time, and the maximum proper time is the path of maximum proper time is going to be the one that that a physical particle takes. Okay, and so proper time can be written, okay, as minus the square root of, I mean, this square root of minus eta mu nu dx mu dx nu. And now instead of parameterizing the trajectory using proper time, I can parameterize it using any other parameter. It doesn't even have to be proper time. So I'll call that parameter lambda. Okay, so I can write it like this. This is another parameter. And I'm free to choose this parameter. Okay, and this equation will take the same form no matter what choice of parameter I use. Okay, so this equation, this action has a symmetry, which is called reparameterization invariance. Okay, that is, you can switch from parameter lambda to some lambda prime, and the form of the equation would stay the same. Okay, so lambda is some parameter that describes the trajectory, and so the trajectory is some x mu, which is a function of lambda. Okay, lambda is one parameter, and it tells me all the coordinates. That is x0, what is the time coordinate as a function of lambda, what is the space coordinate as a function of lambda. Okay, and now the claim is that if I want to find the equation of motion of such a particle, okay, which is going from A to B, all I have to do is for all functions x mu of lambda with the boundary conditions that the initial x mu of lambda at some initial lambda is some x mu of A. This is my starting spacetime point. And my final point is x mu lambda is x mu B, which is my final spacetime point. Okay, so all I have to do is extremize this action. So you can see that this is actually the action that you learned in classical mechanics for a particle in special relativity. Okay, if I extremize this action, the equations of motion that I will find, we won't prove this right now, but you will find exactly these equations of motion. Okay, in fact, you'll find them in terms of lambda. Yeah, okay, in terms of tau as this. Okay, so you'll find exactly these equations of motion corresponding to this action. Okay, so you can try it out or I'll prove it later. Okay, there's a slight trick to proving this. Okay, so you will get these equations of motion, which I'll prove later. And the claim is that the particle then, a free particle, a particle that doesn't experience any forces, okay, that is an inertial object, it takes the longest path through space-time, okay? Or in other words, it takes a path that extremizes the action, okay? So it's not necessary that you have to minimize the action, you just have to extremize the action, which means it could be a maxima, a minima, or a saddle point of the action. You're finding the function x mu of lambda, or x mu of tau, that extremizes the action. Okay, this is the one for which, so you calculate a quantity. This quantity is a Lorentz scalar because proper time is a Lorentz scalar. And this Lorentz scalar, you find the trajectory for which this Lorentz, the trajectory for which this, by trajectory I mean x mu of lambda, the trajectory for which this action, which is a number, is maximum. Okay, so in other words, I have xt, this is a space-time point xa, ta. This is space-time point xb, tb. I want to find, I can draw many possible trajectories to get from A to B, okay? And I want to know which of these trajectories the particle will take. The answer is for each trajectory, I calculate an action. Okay, so each trajectory is some parameterized by x mu of lambda. I can calculate an action for it. So each trajectory is associated with a number. That number is this action. Okay, so the action gives me a single number. I calculate all the trajectories and I find the trajectory which gives me the maximum action. Okay, so S max. That is going to be the trajectory that the particle follows. Okay, it's the one that maximizes the proper time or equivalently the action. Okay. Okay. All right, so I think this is a good place to stop. So we'll take this principle and some of the things that we've learned about regular observers from last time. And what we'll do with this is now we'll try to postulate some principles of general relativity. Okay, any questions here? Have you seen this equation before in your classical mechanics course, this kind of action?
Yes.
You have?
I mean,
This specific action. Sorry, go ahead, Anish.
So, I mean, I think we've not seen this specific form of action in that. Of course, I mean, the integral of the Lagrangian is something that we do usually have, of course.
Mm-hmm. Yeah, this is very similar to, so this is some S of x mu of lambda. And you can write it as some integral of some Lagrangian, which you can think of as dx mu d lambda. It's a function. I mean, it depends on derivatives of x, and it could depend on x as well. And it's an integral over lambda. So lambda is like your time, okay, except it's a parameter of the trajectory. And x mu are your variables. So including your actual time coordinate and your space coordinate, all of these are now variables for your Lagrangian. So you have to find an equation of motion for each of them. Okay, we're going to work more with this action later, so don't worry about it if you haven't seen it yet. Yeah, go ahead, Toshif.
Sir, I had a question that, sir, can we like define an inertial observer in this context as someone, even if the field is not even if the field is not uniform in any arbitrary gravitational field, a truly inertial observer is someone who at any at any given space-time point uses like his metric in his coordinates is the Minkowski metric at a local point. Will that be the definition of an inertial observer?
Yeah, yeah. You could. I mean, a freely falling observer in a uniform gravitational field. Yes, they will. Basically, they will experience locally a Minkowski metric.
Yes, sir. I mean, even if the gravity is not uniform, like even if it's arbitrary, so at every space-time point, to write the ds squared, I mean, he can use in his xt coordinate as ds squared as eta ab dx alpha dx
Yeah.
beta.
Yeah.
So yeah.
Yeah. No, you're right about that. Yes, what you're saying is correct.
And that actually corresponds to a freely falling observer in a uniform gravitational field, but that is a different interpretation. Like mathematically, we can say that that is how a space-time interval will be written by a truly inertial observer, like if he uses the metric as Minkowski metric in his coordinates.
Yeah. So an inertial. Okay. So the equivalence principle is basically saying that there's no difference. There's no way to tell the difference between freely falling in a uniform gravitational field and being an inertial observer. And what we've seen is that you can, if you can change your coordinate system so that locally you have a Minkowski metric, okay, and in fact it's always possible to do this, okay, if you're a freely falling observer, then you can always switch to a coordinate system where your metric locally looks like a Minkowski metric.
Yes, sir. And that observer is the inertial observer, like who uses Minkowski.
That observer is an inertial observer. There can be many inertial observers.
Yes. Yes. At every space-time point, we can do this.
Yes.
Thank you, sir.
Yeah, in fact, we'll use that to build the principles of general relativity. Okay, so the key idea will be we will want to break from just talking about uniformly accelerated observers or uniform gravitational fields, and now we want to talk about the effect of non-uniform gravitational fields. And as we've seen earlier, the effect is tidal forces, right? That is, you'll see if you're in an accelerated reference frame which is non-uniform, like let's say you're dropped in an elevator with two apples hanging next to you, the apples will appear to come closer relativity seeks to describe as a genuine gravitational field. Okay, which is not an artifact of your coordinate system. Okay, if there are no more questions, let's stop here and we'll meet on Thursday. And remember, we have an extra class on Saturday, this Saturday at 11 a.m. Okay, thank you all. Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.